Now we're going to look at actually testing a claim about a proportion. So we'll go through a whole hypothesis test. So some additional notation we need to remember. If we're talking about proportions, then N is our number of trials. The P with the hat is our sample proportion. And remember, if we're talking about proportions, we're really talking about a binomial distribution. So this X here is going to be our number of successes. So whatever it is that we're considering a success, whether it's a baby girl or lessening of cold symptoms or anything like that, this will be how many successes we had out of the N trials. And the P without the hat is our population proportion. This is the number that's in our null hypothesis. Q is just 1 minus P. And here are our requirements if we're going to test claims about a population proportion. We have to have a simple random sample. We have to have the conditions for a binomial distribution satisfied, so only 2 outcomes and so on. And NP and NQ have to both be greater than or equal to 5. This means we have to have at least 5 successes and 5 failures out of all of our trials. Oops. And here's our test statistic formula. And again, this number right here comes from our sample data. This is our sample proportion. And the N is our sample size, or our number of trials. And these other numbers come from our null hypothesis. So the P is the number that's in our null hypothesis. And the Q, remember, is just 1 minus P. Here's an example. We had a study in which 57 out of 104 pregnant women correctly guessed the sex of their babies. So we want to test the claim that the success rate of guesses is different from the 50% success rate we would expect with just random chance guessing. We're going to use a 0.05 significance level and the p-value method to test this claim. So our requirements, they either got it right or they didn't, so we only have 2 outcomes. We had a fixed number of trials, 104, and we had at least 5 successes and at least 5 failures. So since our original claim is that the success rate is different from 50%, different, again, means not equal to. So we'd say that P is not equal to 0.50. Since that does not have an equals in it, that is going to be our alternative hypothesis. And once we have that, our null hypothesis is just the same, only with an equals, replacing our inequality. We already know our significance level is alpha equals 0.05 because the problem told us that. And step 3 is to find our test statistic. So here's our formula. And notice that for the p-hat, the sample proportion, we're putting in the 57 out of 104. That's how many of the women successfully guessed the sex of their babies. So this was the number of successes over the number of trials. And the p of 0.5 came from our null hypothesis. The 104 is our sample size, and again, here's the p of 0.5 and the q, which is 1 minus p. So our test statistic comes out to be z equals 0.98. And the z, remember, tells you to use your z-scores table or your normal CDF function. Now, since our alternative hypothesis had a not equal to, then that means that we have a two-tailed test. So we're going to draw a picture of our distribution, put our test statistic on it, find the probability of z being in that tail, and then we're going to multiply that probability by 2 to get our p-value. So here's our picture. And remember, this is a standard normal distribution, so we have 0 in the middle. Here's our test statistic of 0.98. And since that's to the right of 0, then we're going to look at the right tail. It's just whatever tail it's already in is the one that we look at. So we want to start out by finding the probability that z is greater than 0.98. Now, since that's a greater than, in our table, we would have to look up 0.98 and subtract from 1. So that's what they're doing here. This area over here is the 0.8365. If we subtract that from 1, we get 0.1635. So that's our probability. And to get our p-value, we would have to multiply that by 2. So this gives us a p-value of 0.3270. And if you use your calculator for this, you get a slightly different value for your probability, so your p-value would come out just a little bit different. Now, to get our conclusion, we're going to compare our p-value to our alpha. So what I like to do is just write down the 2. You can either, let's just write 0.327 since they both round to that. So here's our p-value on this side, and then our alpha was 0.05. If we're comparing these two, then this one on the left is definitely bigger. So we would have our p-value is greater than alpha. And that told us that our conclusion would be fail to reject the null hypothesis if our p-value was larger. Now remember that the fail goes with the not in our final conclusion. So if we fail to reject the null hypothesis, that says there's not sufficient evidence to support the claim that women that guess the sex of their babies have a success rate different than 50%. So what that's really saying is that they're not any better at guessing the sex of their babies than if they just took a random guess. Now in some problems, as we've already seen, our sample proportion will be given to us directly as a percentage. So for example, if we say 10% of the sports cars are red, that's already our sample proportion. And all we have to do is change that to a decimal value. And in some cases, like that last example, it will be given to us as a number of successes and a number of trials. Now finally, we're going to look at testing claims about a mean. And in this one, again, we use the t-distribution, just like we did for confidence intervals about a population mean. So the notation we have, n is still the sample size, x bar is the sample mean, and we're going to use mu or mu with the little x bar as our population mean. Most of the time we'll just use the mu. And the requirements here aren't quite so much as for the population proportions. We have to know that we have a simple random sample. And in this case, we're assuming we don't know the population standard deviation. And that's the normal case because usually we don't. And the last one is that one or both of these conditions have to be satisfied. Either the original population is normally distributed or that our sample size is greater than 30. Here's the formula for our test statistic. And again, the x bar right here, the s, and the n all come from our sample data. The mu with the little x right here comes from our null hypothesis. So in this formula, this is the only number that comes from the null hypothesis. Now here's an example. In this one, we're talking about the mean weight of men. So we have a sample of 40 men, and their mean weight was 172.55 pounds. Their sample standard deviation of their weights was 26.33 pounds. We're going to use this to test the claim that men have a mean weight greater than 166.3 pounds using a 0.05 significance level. So first, our requirements. We did have a simple random sample. We don't know our population standard deviation, and our sample size is greater than 30, so that's all we have to worry about. So first, to find our hypotheses, the claim was that the mean weight was greater than 166.3 pounds. And again, for our mean right here, we're just going to use mu. So since this one does not have an equals in it, that automatically tells us that that's going to be our alternative hypothesis. So we can write down that H1 is that mu is greater than 166.3. For our null hypothesis, we have the same symbol, same number. We just replace our inequality with an equal sign. And we already know that our significance level is 0.05 since that was given to us. Now we want to calculate our test statistic. Here's our formula. So we're using our sample mean of 172.55. This number, remember, is from our null hypothesis. This is our sample standard deviation. And this one is our sample size. And if we calculate that out, that gives us a test statistic of 1.501. Now we're going to use the traditional method for this, so we need to find the critical value. Now remember, if we're using the t-table, we have to use this degrees of freedom to tell us which row to look in. Degrees of freedom is going to be n minus 1. So since our n was 40, our degrees of freedom will be 39. And what we want to look at is, since we have a one-tailed test, we want to look in our table where it says area in one tail, and the area that we want is 0.05. So that's the column that we'll look in. We'll look in the row that says 39 degrees of freedom, and that gives us a critical value of 1.685. So what this is going to look like, the t-distribution looks for the most part like a normal distribution. So we still have 0 in the middle, and we have 1.685, and since this was a right-tailed test, then our critical region goes from there to the right. So if our test statistic comes out to be in this region that I've got shaded, then we'll get a conclusion to reject the null hypothesis. Otherwise, we fail to reject. So if it's over here, we say we fail to reject. Well, they have a prettier picture than I did. But again, here's our critical value of the 1.685. Our test statistic was the 1.5 something, so that's over here. It is not in our rejection region. So our conclusion is that we failed to reject the null hypothesis. And remember, the fail means that there's not sufficient evidence. The fail and the not go together. So there's not sufficient evidence to support a conclusion that the population mean weight is greater than 166.3 pounds. Now the p-value method with the t-table is a little bit tougher because the t-table doesn't have as many values in it as our z-scores table. So all we can do using a table for this is to find a range of values. So we're going to do a few examples of this so that you can see how to do it. And this is if you don't have access to actually a TI-84. Even the TI-83s don't have this function for the t-distribution on them. So let's say we have a left-tailed hypothesis test, sample size of n equals 12, and our test statistic is t equals negative 2.007. So here's a little cutout from the t-table, and if we have a negative test statistic, if we're looking in our t-table, we just turn it to a positive value. So what we want to look for is our degrees of freedom would be 11 because our n was 12, and we're just going to look in this row. Since we had a left tail hypothesis test, we're looking at the area in one tail. So we want to see where this test statistic fits in between these numbers. The 2.007 would actually be in here, would be between the 2.201 and the 1.796. So that says that our area would be somewhere in between 0.025 and 0.05. So that means our p-value is between 0.025 and 0.05. Now let's go back and look at the next problem. In part B here we had a right-tailed hypothesis test. Sample size was still n equals 12, and our test statistic is 1.222. So again, we are looking at the area in one tail. We're looking in the same row because we still have n equals 12, so our degrees of freedom is 11. And the 1.222 in comparison to these numbers would be over here, because notice that these are going down. So this would be over here to the right of the 1.363. And what that tells us is that our p-value is somewhere from 0.1 up, because notice here these areas are going up, so that means that our p-value is going to be greater than 0.1. And the final one, in this one we have a two-tailed hypothesis test. We still have n equals 12, and this time our test statistic is negative 3.456. And again, we're just going to use the positive value of this because that's what we have. in our table. So 3.456 would be, in comparison to these numbers, would be over here. And remember, this time we had a two-tailed test, so we can make this a little bit easier, but just by looking at the area in two tails. And the 3.106 gave us the 0.01, and we're to the left of that. So that means that our p-value has to be from there on this way, which means it has to be less than 0.01.